In this video, I'll show you how to build and use the PUMA Augmented Reality or AR Projector. The concept of visual AR microscopy using a heads-up display or HUD, as well as details on how to use PUMA as a platform for developing your own custom AR applications, was dealt with in the video on augmented reality and the trinocular camera port. So see that video for details. PUMA uses a low-cost 1-inch square programmable TFT display screen like this one as the basis for generating the HUD. In order to turn this display into a HUD, I had to do two things. First, project the image of this screen onto the same focal plane as the image of the specimen formed by the objective. This is done with the lenses of the AR projector and the beam splitter in the advanced filter block, as shown in this diagram. We'll come back to this in a moment. Second, because the image is reflected up the optical tube by the beam splitter, I also had to program the display to use mirror writing, so it will appear correct when viewed with an eyepiece, and you will need to do likewise if writing your own custom applications. Note that this mirror reversal works for all PUMA configurations that use an ocular lens, because the number of reflective surfaces in the beam path always sums to an odd number. However, apart from the simple monocular seam mount configuration, anytime you use a direct seam mount camera, there will be 0 or an even number of reflective surfaces in the beam path, so the recorded image in these seam mount cameras will retain this uncorrected mirror image. This is easily remedied, however, by using the camera's inbuilt H-flip control, or using software to mirror flip the video after recording. Now, returning to the optics of HUD projection, recall that the AR projector takes the image from a TFT screen and projects it such that it comes into focus in the focal plane of the ocular. When you think about that, it is clear that the AR projector is simply doing for the TFT screen what any objective lens does for the specimen on the stage. Thus, we see that the AR projector is just a custom objective lens, allowing you to see the TFT screen specimen superimposed on the image of the stage specimen, which is projected to the same place by the microscope objective. So what is the magnification of this AR projector objective lens? To answer that, first let's look at what magnification means in practice for any objective. In fact, this is very easy to demonstrate using PUMA. Here I use a slide of allium root tips as the specimen. To see the primary image projected by the objective lens, I'll use this projector screen made from a piece of tracing paper with calibration marks printed on it. The circles are 1 centimeter apart and the small divisions are millimeters. Now I'll remove the ocular head from the scope and position the projector screen at the place where the objective focuses its image. There. Now, it's awkward to hold this by hand, so I've prepared an attachment which allows me to rest the screen on it at just the right height. I've made this attachment available on the GitHub page in the monocular FreeCAD file if you want to use it to do your own demonstration, such as for teaching the principles of microscopy to students. So that you can see relative measurements more easily, I'll replace the biological specimen with this stage micrometer slide that has a 1 mm line with subdivisions etched onto it. So now you can see two things. First, the actual full diameter of the projected image is about 35 mm. This is not related to magnification, but it determines the maximum field of view you can get with any objective. The important thing with regards to magnification is the size of the object in the projected image compared to the actual size of the actual object. Here you see the 1 mm line now occupies 10 mm, so it has been magnified 10 times, and yes, the objective I'm using is a ×10 objective. With a ×4 objective, the 1 mm line spans 4 mm in the focused projected image, and so on. For any objective of magnification x, the projected image shows any feature in the object of actual size y with a projected image size of x times y. So that's magnification dealt with. What about the field of view? Well, the maximum possible field of view is limited by the objective, how big this projected disc is. However, the actual field of view is determined by the ocular lens, that is, how much of this disc the eyepiece can capture and present to your eye. The eyepieces used with PUMA fit a 23.2mm diameter barrel, and the PUMA HUD is designed to be used with eyepieces that have a field number of 20mm. This field number is the physical size of the clear aperture at the focal plane of the ocular, and that is the actual size of the disc of light that you will see when looking down the eyepiece, magnified further, of course, by the eyepiece lenses. This aperture is often produced by a diaphragm placed at that plane, which gives the field its crisp round edge. So, 20mm is the maximum diameter of this projected image field you can see with these oculars. All of the objective produced image outside that 20mm disc will be cut off from your field of view. Now we are in a position to understand the magnification of the PUMA AR projector. Recall that the TFT screen of the HUD is 25mm square, although the actual pixels cover 24 by 24mm. When designing the AR projector, I had two goals that needed to be balanced. One, to use as much of the TFT screen area as possible so as not to waste pixel resolution, and two, to allow the HUD to fill the whole microscope round field of view. So the compromise position that best fit these goals was to project the TFT screen such that the flat edges of the screen just reach the outer limits of the field of view, and only use the circular central area of the screen for the HUD. This wastes the corner pixels of the screen, but that can't be helped if we're to fill the whole microscope ocular field with addressable pixels. Dimensions-wise, this means that the 25 by 25mm square TFT image must be shrunk down to a 20 by 20mm optical projection image at the focal plane of the ocular. So I designed the lens system to effect a 0.8 times magnification, and that is demonstrated here. So, the AR projector is effectively just a 0.8 times objective lens. Unlike most microscope objectives, however, the AR projector has some built-in magnification and focus distance adjustment mechanisms, which you can use to ensure parfocality with the main microscope objective, and also you can adjust it to project 10mm further away for use with 170mm tube length objective lenses, as well as the RMS standard of 160mm. Before I move on to the next part of this video, I would ask that if you like these PUMA videos, please take a second to support the project by clicking on the big red subscribe button and give the video a thumbs up. If you have social media accounts, also please share these videos on them using the YouTube share button. Okay, now back to the rest of this video. The AR projector is made using two high-quality achromatic doublets with partial aspheric properties as well, one concave and one convex. Having said that, the AR projector does still suffer from some residual aberrations, but the cost of DIY production with these lenses is still much cheaper than for more highly corrected commercial objectives with magnifications of less than 1. So, the PUMA design is, as always, an acceptable compromise between affordability, portability, and performance. Now, you could make a projector from just a single convex lens, but this would require a very long light path that would detract from portability, and I included the concave lens to shrink the unit down without needing mirrors and prisms to fold the light. We've noted that the AR projector is essentially just a 0.8 times objective lens, and, as such, it will project an image of any specimen placed at this plane here. For use as an AR projector, we place the TFT screen at this point, with this bracket that allows for X and Y centration adjustment. However, I've also made this alternative slide holder, which can be used to hold a standard 25 by 75mm microscope slide, so you can use this as an ultra-low power microscope objective. It's uncommon and very expensive to get microscope objectives with magnifications less than 1. So this is a very useful module for general overview observations of specimens before moving them to the stage for more magnified viewing. For best viewing results with this setup, be sure to block all light coming from the main microscope objective. You can do that with a solid opaque black filter in the lower filter slot of the filter block. Whatever specimen you use, slide or TFT, the specimen is held in this adjustable draw tube attachment, which can be angled slightly for XY adjustment and pushed in or out to effect a focus adjustment and as part of the zoom adjust mechanism. The other main adjustment that affects zoom, that is magnification, is the distance of the concave lens from the convex lens, which can be adjusted in 2 ways. One is how far into the holder you sight the concave lens during construction, and the other is the adjustment afforded by this thread and lock nut mechanism. I'll discuss this in more detail later. One limitation of this small TFT-based HUD system is that the illumination is limited in brightness to what the TFT backlight can produce. This may require you to lower the scope light source level with neutral density filters or by reducing the current to the LED to ensure good visibility of the HUD. If this is unacceptable, then there is the possibility of removing the inbuilt backlight of the TFT and rigging up a separate brighter light source, but I haven't done this for the standard PUMA system. It would be up to you to make such a customization if your project requires it. Be warned that removing the backlight from these small TFT modules is a very delicate procedure and can easily break the screen. I'll describe how I do it in a separate tutorial on the PUMA SLM. These are the parts and the tools you'll need to build the PUMA AR Projector. As always, begin by cleaning up the parts from any stray plastic, supports, etc., and scrape and brush the threads till they all fit well. Do this and clean away any dust before handling any of the lenses. Now assemble the TFT DrawTube F module by inserting the M3 nuts into their pockets and hold them in place with 3 M3 thumb screws made as described in previous videos. Insert the thumb screws into the nuts, but not further down to deform the plastic at this stage. Now, insert the TFT draw tube sheath, ensuring that these plugs are sighted over the M3 nut pockets, so that they go into the pockets when fully inserted. You may need to scrape and brush both the outer aspect of this sheath as well as the inner aspect of the draw tube, because this is a very tight fit. When the sheath is fully inserted, you should remove the thumb screws and use a regular bolt with an Allen key or a screwdriver to screw the bolt in further till you see the plastic deform inwards. This can be very difficult, so you must ensure you apply inwards pressure while turning so all the force is not taken by the M3 threads, or the metal threads may be destroyed. This can hurt your fingers if you use your bare hands and the thumb screws, which is why I advise you to do this with a separate screw and screwdriver. Once all 3 positions have been prepared in this way, you can reinsert the thumb screws. Ensure the 90-degree connector is attached to the TFT screen as shown, then mount the TFT screen onto the TFT mount module with the M2 nuts, bolts and washers. The washers only go on the side of the bolt heads, not on the PCB side. The design of the holes allows some lateral X adjustment as shown. Keep these bolts loose until after you have effected the proper XY adjustment later, but in any case avoid over-tightening or you will bend and eventually break the PCB. Insert the 14mm long M3 bolts without washers into these posts and mount them just poking through the holes for them in the TFT draw tube F assembly. Then manipulate an M3 nut over the end of each bolt and manually thread it on until it just catches a thread. This can be quite a tricky maneuver. Once all 3 nuts are on, move the whole assembly further in till the posts contact the draw tube. Then thread the nuts all the way in by finger, but don't tighten them. The design here allows some vertical Y adjustment, as shown. Now we turn our attention to mounting the lenses. Before handling any optics, make sure there are no blebs of plastic or irregular seams on the ledges that support the lenses, because if either lens is not inserted fully flat in its mount, this will deviate the image beyond your ability to compensate for with the TFT XY adjustment described above. Insert the screw-in CC retainer module into the CC mount draw tube module as shown, with the slits for the insertion tool going in first, so that the flat surface that was in contact with the print bed will be facing the concave lens when it is inserted. The default position for the retainer is to screw it in fully, then unscrew it by half a turn if you only intend to use 160mm tube length objectives, or 2.5 turns if you want to use 170mm tube length objectives. This latter setting of 2.5 turns can also be used with 160mm objectives because you can compensate for it later with the CXCC connector module and lock nut, so you may want to use this setting by default. Now, insert the concave lens into the CC mount draw tube as shown, with the thin groove on the metal lens sheath facing closest to the convex lens, that is, facing away from the TFT screen. If it goes in all the way to the retainer, that's great, but if not, it is sufficient for now that it goes in far enough to reveal a few threads on the draw tube. Avoid touching the lens surface with your fingers. You can use a piece of lens paper if you need to push it in manually. It should be a relatively easy fit. If not, you may need to remove the lens and scrape or sand the thread of the CC mount draw tube a bit more, then try again after cleaning away any dust. Now thread in the CXCC connector with its flat surface facing the concave lens and screw it in till it contacts the concave lens and pushes it firmly against the CC retainer. If, for reasons of focus or zoom, you want to bring the concave lens closer to or further away from the convex lens, you can do that by adjusting the position of the CC retainer in the draw tube, but do that only after you first remove the concave lens from the barrel to avoid the possibility of slipping with your adjustment tool and scratching the lens. Over the CXCC connector, thread the CC lock nut. This should go in all the way down, but if you need to move the concave lens further away from the convex lens, you can do that by unwinding the lock nut by the desired amount. For example, if you used the 2.5 turn setting for the CC retainer above, but you want to use 160mm objectives, you should unwind the lock nut by 2 full turns to compensate for the extra closeness of the concave lens to the convex lens. The zoom or magnification will be very slightly lower than with the half-turn setting of the CC retainer, but still very close to filling the whole microscope field. Thread the 46mm ferrule over the connector till it contacts the lock nut and tighten them together. Make sure you insert this ferrule with the recess in the body of the ferrule furthest away from the draw tube. The position of this recess is important because it allows room for the protruding part of the front focus post when the stage is lowered to its lowest levels. Now make the convex lens assembly by inserting the convex lens into its holder as shown, with the thicker lens element of the doublet facing the lip of the holder as shown. Then hold it in place with the push-fit CX collar. Basic assembly and usage instructions for the stay clip and thumbwheel system were given in the video on epi-illumination. However, I've made some improvements since then. First, I now recommend use of a 14mm long M4 screw for the front of the focus plate and not a 12mm screw. This is because the correct position for the stay thumbwheel is quite high up and it doesn't always catch sufficient threads on the shorter 12mm screw. The second improvement is the use of a lock nut for increased stability. To make the lock nut, take a CND adjust thumbwheel model and insert an M4 nut, 3mm long, into the recess instead of an M4 hex bolt. Put this lock nut onto the M4 screw in the front of the focus plate with the nut facing downwards and thread it all the way down. Now thread on the stay thumbwheel as shown until it contacts the lock nut. Then raise it by about 2 full turns. Not only will this automatically put the stay thumbwheel at about the correct height to accept the stay clip, but also, once clipped in, you can raise the lock nut and tighten it against the stay thumbwheel for extra stability. One other significant change is that now I do away with a separate articulating clip and clip lock and replace this with an all-in-one clip that incorporates the clip lock into a single print. To attach the AR projector to a PUMA microscope, you'll need the advanced filter block installed. If you're not using the trinocular camera port or epi-illuminator, it's advisable to have a light sink on the epi-illuminator port. Raise the stage with the focus gears till it is above normal focusing distance. Ensure the stay thumbwheel is correctly positioned, as discussed earlier. Screw the convex lens in its holder all the way into the front port of the advanced filter block. Put the AR clip on the 46mm ferrule and thread the rest of the AR projector all the way over the convex lens holder till it is tight against the filter block, but do not over-tighten. Clip the stay clip into the stay thumbwheel receptacle and rotate the thumbwheel by a quarter turn to lock it in place. Then hold this assembly firmly with the stay lock nut. Remember to undo this clip whenever you need to remove the optical tube from the focus plate or remove the AR projector. Fix the stay clip in place with the clip lock and thumb screw. The AR projector is now properly attached to the scope. What remains is for you to center and focus the image with the correct zoom in the ocular field of view. To align and focus the HUD image, you'll need a specimen on the stage with an objective lens in place. Any magnification should be okay. and you must focus the image of the specimen. The light source you use is up to you, but you must have some means of dimming it sufficiently so that the HUD can be clearly seen when it is switched on. This usually means using a strong ND filter in the PUMA illuminator or lower filter slots, or turning the LED current down. Do not use an ND filter in the upper filter slot because that will dim the HUD image. Attach the TFT display of the HUD to a display driver and switch on the display. If you're using the PUMA control console, you must connect the TFT to the console before you power up the console. See the PUMA control user manual on the software section of the GitHub page for details of how to connect the TFT to the console. Now, look down the ocular and see if the HUD is centered and in focus. The PUMA control software boot-up screen is sufficient for this purpose because it has a circle around the periphery which should be just within the field of view if the correct centration and zoom are used. If the HUD is not in focus, you can move the draw tube in and out to achieve focus. This should be possible. If not, it means that some aspect of the microscope or the AR projector is not put together or set up correctly. It may be that you have the ocular cap gap or OCG of the microscope ocular cap not set correctly. Or maybe the objective is not screwed in fully, or maybe you are using the 170 ocular cap with a 160mm objective, or vice versa. If all those things are correct, then it may be that the lenses of the AR projector have not been sighted correctly. See the instructions I discussed previously to troubleshoot that. You can effect some additional focus adjustment by altering the distance of the concave lens to the convex lens by altering the position of the lock nut and 46mm ferrule, or by changing the position of the concave lens in its holder. Once focus and zoom of the HUD are satisfactory, you should then concentrate on centration. This can be tricky because any slight deviation of either lens from the perfect vertical orientation and any slight deviation of the 45-degree beam splitter in the advanced filter block can throw the image off axis. There is no adjustment for the filter block beam splitter angle, so we can't effect any corrections there. As for the lenses in the AR projector, your best chance to get those right is during construction. The first and easiest adjustments to try are the XY adjustments of the TFT screen in its holder. If these are sufficient to center the HUD, that's great. Just fix the TFT in place by tightening the bolts and screws, but be very careful not to tighten the M2 screws fully, because you will break the TFT PCB and it will stop working permanently. If centering the TFT alone is not enough, you can effect more adjustment by angling the TFT draw tube on its mount. If the above two adjustments are together not enough, it may be better to take the projector apart and check the lens mounts again for irregularities, especially the convex lens mount. However, there are a couple of additional adjustments you can make. First, it may help to change the rotational position of the CC mount draw tube on the 46mm ferrule. This will require you to unscrew the lock nut a little and retighten it. If the concave lens is not perfectly vertical, you may find a rotational position that shifts the image enough to get alignment with the other adjustments already described. If all the above are still not sufficient, then, as a last resort, you can alter the angle at which the entire projector connects to the filter block. To do this, switch off the TFT, disconnect it from its ribbon cable, and release the AR clip lock. Then unscrew the 46mm ferrule and all of the rest of the projector with it from the convex lens mount. Now unscrew the convex lens mount from the filter block slightly and insert a thin sliver of plastic at one point between the convex lens mount and the filter block before retightening. This will force the convex lens holder to be at an angle to the filter block. Choose the position of the inserted sliver of plastic such that the tube angles in a direction that solves your alignment issue. Then reconnect everything and recenter using the methods above. Once XY centration and focus are set, you can clip the light shield in place. This fits over the 3 M3 posts of the TFT mount. You'll notice that the clips are closer to one edge. That is the edge furthest from the microscope, and it lines up with the external surface of the TFT mount. First clip the top clip in place, then the 2 sides, like so. Your AR projector is now complete and ready to use. Detailed use of the stock PUMA control software functionality for this unit is given in the user manual on the GitHub page. You can also develop your own custom applications as required. Thanks for watching.